Today is 16. It's dark.
Okay, so we should talk about today the second law of thermodynamics. And I already told you last time that the second law of thermodynamics comes from, is expressed in two statements, one by Kelvin and one by Carnot. And since these two statements refer to the working of an engine, right? So let me first, before starting, explain what is an engine, what is a thermal engine, and how we think about it. Well, a thermal engine is an engine that essentially operates between two reservoirs, extracts some work from one reservoir, extracts some heat from one reservoir, releases it to another one, and does some work in between. So typically, it's represented by this graph. This is a quite standard graph in thermodynamics, in which you have a warmer reservoir, so T2, the temperature T1, and then some work is done, some heat Q2 is extracted, and some heat Q1 is released to a colder reservoir. So the important thing is that T2 is greater than T1, right? So this is an engine that does work. There's also an engine in which you reverse the sign of the arrows, right? Which is an engine that will take heat from a colder reservoir and release it to a hotter reservoir while doing some work on the working substance of the system. So it's what happens when you do things the other way around. So let me draw it. Something like this. So this is something very important. Not now. It's going to be important. Well, it's even important now, but it's going to be much more important in May and June. So it's called, how is it called? What is this? Refrigerator, right? Refrigerator. All right, so when you think about an engine, so this is a typical drawing of a thermal engine. So there is a concept in thermodynamics which is called the efficiency, right? Now, efficiency is something very, very practical, right? He's telling you, as I was explaining to you last time, he's telling you how much something you get from your money, for your money. So in particular, if you have an engine of this type, you want it to do some work, right? For example, you have a car. And then you will define the efficiency of this engine as the work done divided by the heat that you took from the first reservoir, right? So the heat that you take from the first reservoir is, in a sense, the money that you have to spend, right, to heat up your, I don't know, your steam engine, or to, I don't know, to put fuel in your car. And the work is what the engine is capable of doing. It's what is releasing, right? Now, of course, I mean, if you have a refrigerator, the money you spend is not Q2. What is the money you spend? Is work, right? The money you spend is to put the plug of the electricity in, is the electricity that you have to pay in order for the motor to work and to transfer heat from inside the refrigerator to outside, right? So therefore, the efficiency or the cooling power of a refrigerator is going to be expressed in a different way. But we don't care. I mean, we're going to focus mostly on thermal engines at this time. Now, among all possible engines, there are some special engines in which are called reversible ones. So what does it mean to be reversible? Transformation, right, is reversible whenever you go from A to B, and then by reversing the sign of, I mean, by going backward in time, you can go back from B to A. You can reverse the direction of your transformation at each instant of time. Right, so you can trace back your steps. Now there is some confusion sometimes among students. I don't know, can you? Yeah, you can see me from the. So, and the confusion is the following. So let's say, look at the lights above you. You turn it on, and I turn it off. Was it a reversible transformation? Why? Well, you see the same as, now it's state A, state B, state A is the same as before. Is it reversible?
I'll say no, but
You say no, and you're right. But why no? You're absolutely right. But believe me, when I ask this question, I give a course on non-equilibrium physics at CISA. And I ask this question to students at CISA in one of the first classes, and they always get it wrong. So don't worry. I mean, it's a simple but advanced question, apparently.
is it because the heat that was released cannot return?
The what?
So we turn on the lamp, right?
Yes.
And then we turn off. But
Yes.
the heat that was just released cannot
Yes,
return.
absolutely. That's exactly the point. So when you turn on the light, when you have it off, you turn it on and you see some light. What is the light that we see? Are photons, right? Photons, heat. Well, if you touch it, it's going to be warm. But the photons are going to travel from there. I don't know, this is probably a neon lamp, so there is a discharge, and then photons are being emitted. Then you turn it off, and you say, aha, it's the same as before. No, it's not the same as before. Because the photons that you emitted are not going back to the lamp. They have been emitted. They are being absorbed by, I don't know, by the screen, by the table, by whatever, by your skin. But they're, the state of the universe is not the same as it was before. So it's not a reversible transformation. It's not a reversible transformation because essentially the amount, well, we will see it later on, but the amount of work that you're doing is not just the difference in free energies between the final and the initial state. There is some dissipation associated to this transformation. Anyway, reversible engines are special. Okay, and now we understand what is a reversible engine, and we understand that that is not a reversible transformation. Okay, have you ever seen a reversible engine in your life?
Guess not.
Most probably no. It's an idealized limit, right? It's a limit in which, for example, sometimes people think about reversible transformations as quasi-static transformations, right? In which you move so slowly that in practice you're in equilibrium at all instants of time. And then if you move backwards, since you're quasi-static, you trace the path back. You understand that if this is the kind of reversible transformation you want to make, if you make an engine of this type, it's going to take forever to go through the cycle, right? It's like having a piston of a car that does, and the car goes at 1 centimeter per hour, very fast, like a turtle car. So reversible engines are not very useful engines for all purposes because well, we will see later on. Anyway, okay, now that we understand what are engines, let me say again what are the two statements of the second principle of thermodynamics. A transformation, so this is the Kelvin statement. Kelvin said, the transformation whose only effect is the conversion of heat into work from a source at fixed temperature, heat taken from a source at fixed temperature into work, it's impossible. Again, if you want to remember this statement, the pen does not jump up from the table. That's the statement. I mean, you cannot absorb heat and do work only. It's impossible. The Clausius statement is that there is no a transformation whose only effect is to extract heat from a warmer reservoir and deliver it to a colder reservoir, to a warmer reservoir, so T2 is smaller than T1, T1 is smaller than T2, this transformation is impossible. Now notice one thing. It's important to keep in mind this word only. So both statements you have a transformation whose only effect is the transfer of heat from a colder reservoir to a warmer reservoir is impossible. Why? Because we know pretty well that if a transformation that transfers heat from a colder reservoir to a warmer reservoir is possible, it's the refrigerator, but in that case, you don't have just a transfer of heat. There is also another effect, which is the fact that you have to do some work on the working substance of your system. All right.
Professor?
Yes.
Can you explain the difference between quasi-static and adiabatic?
Well, adiabatic, strictly speaking, is that you're not releasing. Okay, it's a messy situation, and I understand your question because it's I always mess up with these words myself. So adiabatic means, strictly speaking, in thermodynamics, that you're not transferring any heat in a transformation. Now, in practice, quasi-static, does not really mean this. Quasi-static means that you're staying in thermal equilibrium at all the instants of time through the transformation. Now, I'm not sure it's... Look, let me think about this and give you a proper answer, because I'm going to make your head messier and my head as well. Okay? So I have to formulate an answer properly. And but I have to think about it. Okay, so I'm sorry that I have to formulate things properly. Otherwise, I will just create only confusion. All right, but in principle, we understand the difference in the words. I mean, one is to refer to the fact that you're not transferring any heat, and the other one is the fact that you're going very slowly. Now, what is the connection between the two? I have to think carefully. Okay. All right. So now I told you that. So these are the two statements of the second principle of thermodynamics. And now comes a bright guy, a bright French guy, French engineer. It's practically probably the only useful thing that was ever done by an engineer in science. I'm sorry, I know that this is going on YouTube, and you know it's going to it's a dangerous statement, but all right. So anyway, it's a joke. Don't be afraid. It's just a joke. I have other jokes about chemists as well. Sadi Carnot. Sadi Carnot. And Sadi Carnot had a brilliant idea, really brilliant. The brilliant idea was the following. If you have an engine that operates between two reservoirs at temperature T2 and T1, okay, there is one engine that has the highest efficiency, which is called the reversible cyclical engine. Okay, so you make a cycle and you make it in a reversible manner. So you make sure that you can revert it and go back at all steps. You make all reversible transformations. And in particular, the Carnot efficiency is 1 minus T1 divided by T2. Okay? So in practice, the way I wrote it tells you also that this statement that is so universal, I mean, it doesn't tell you which cycle, right? Don't get confused between the so-called Carnot cycle and this statement. So the statement is any reversible engine, cyclical engine that operates between two thermal reservoirs will give rise to this efficiency. Any. Doesn't matter whether you choose two adiabats and two isotherms or two isocores, two isotherms. Any cyclical engine, reversible cyclical engine will give rise to this efficiency. And the proof that so the proof of this statement is has to be made in two steps. Step number one, we have to prove that the reversible cyclical engine has the highest possible efficiency. And if you do, and if this is not true, then we have some contradiction. Okay, so this is step number one. Reversible cyclical engines have highest efficiency. And then the second statement, again, And then the second statement is that, and in particular, since reversible cyclical engines have the highest possible efficiency, this means that all reversible cyclical engines working between two temperatures have the same efficiency, right? So this is a corollary. We want to use the terminology of mathematicians. And then Carnot invented something called the Carnot cycle. I will tell you later on what it is, but I'm sure that you know what it is and you've calculated it 2,000 times. And for the Carnot cycle, we will be able to prove that indeed T mu C is equal to 1 minus T1 divided by T2. Therefore, since this is the efficiency for the Carnot cycle, it has to be the same for all reversible cyclical engines operating between these two temperatures, and this completes our proof. Okay? Now, this is a very interesting and non-trivial statement. I mean, the fact that I remember that when I was in high school, I was very disturbed by the fact that you could not get something with higher efficiency than the Carnot efficiency. But, you know, deep inside, the statement is connected to the second principle of thermodynamics. There are certain processes that are impossible. In particular, you cannot have a perpetuum mobile, which does work forever without dissipating heat in practice. So it is connected to this kind of thinking. Now, let me show you through the proof of statement number 1 how it works. It's actually quite a nice proof of the story. Suppose that there is an engine operating between these two temperatures that has an efficiency larger than the Carnot efficiency, right? So the engine, we call it prime, and the efficiency is greater than the Carnot efficiency. Then, if this is true, we can do the following. We can take our two reservoirs, the one at temperature T2, the one at temperature T1, and then make a chain out of these two engines. So essentially operate first with the engine number, with the prime engine, the one with higher efficiency, and then use the heat W to operate the Carnot engine in reverse. Because the Carnot engine is a reversible engine, so I can operate it in reverse and it's going to work. That's nice. So let me do this. All right. Now, the fact that mu prime is greater than mu, so mu prime is going to be equal to the work divided by Q prime 2, right? And this is greater than the work divided by Q2, which is the Carnot efficiency, right? Now, this implies that Q prime 2 is smaller than Q2. Since you're doing the same work, and one is more efficient, then you're paying less for the one that is more efficient, right? So the work that you're doing on the more efficient engine, sorry, the heat that you're taking from the hotter reservoir in the more efficient engine is larger than Q2, right? You agree?
Which one is the hotter?
Hotter is 2. Let me use colors. This is hot. And this is cold. Okay? All right, so let's move on. Now that we know this, W, the work, is equal to Q prime 2 minus Q prime 1, and is equal to Q2 minus Q1, right?
Yes.
But therefore, Q prime 2 minus, Q2 minus Q prime 2 is equal to Q1 minus Q prime 1, and is greater than 0, right? No, it's actually the other way around. I apologize. Q2 minus Q prime 2 is equal to Q is equal to Q2 minus Q prime 2 is equal to Q1 minus Q prime 1. That's correct. Now, then, what does it mean? It means that overall, what I have is I constructed, by making a chain of these two engines, an engine whose only effect in this combined cycle is to transfer some heat from a colder reservoir, T1, to a hotter reservoir, right? Because overall the balance of heat that is exchanged is in favor of the hotter reservoir, right? So I violated Clausius statement, second principle. And therefore, since I violated the second principle of thermodynamics, this is not possible. And there is no engine that has an efficiency that is greater than the Carnot engine, than the reversible engine. Okay? It's a beautiful state. It's a beautiful proof. I like it. Right? It's nice. It's very physical. It tells you, look, if there would be something that would have a greater, you would be able to do the impossible, but you cannot do that. By the way, I didn't prove that the Clausius and Kelvin statements are equivalent, but it's, you can find it in any textbook on thermodynamics. So you agree with me? You agree, right? You agree. You don't? You want to do like me and when I was in high school and challenge Carnot?
Yeah.
Unfortunately, it's impossible. There's no way to challenge Carnot. It's correct. All right, so this is the first statement, right? Now, let's go now with the second statement, proof of 2. Now, I said that the first statement proves that for any reversible engine, you will get the same efficiency, and that's the Carnot efficiency, right? So it's going to be just of course, obviously, it's going to be just a function of T2 and T1, because these are the only properties that I'm fixing. But which function, I don't know at the moment. Therefore, I have to cook up an engine, which is a reversible cyclical engine that works, operates between these two temperatures, and that allows me to calculate this efficiency, right? So Carnot came up with this idea of using, first of all, choosing a very peculiar working substance, which is, so the working substance is our beloved ideal gas. It doesn't have to be. Not to get confused on this point. All reversible engines operating between these two temperatures have the same efficiency. So it's not that I have to have an ideal gas sitting there in order to have maximum efficiency. Actually, I remember an exercise in which you had to do the Carnot cycle that I will tell you in a second with a van der Waals gas, satisfying the van der Waals equation of state. Nevertheless, you could prove that the efficiency was still given by the formula that we saw before. Okay, and this has to be. I mean, if you get something else, it's wrong. All right. So, but we choose this because it's simple. And second, we choose the cycle as a very special cycle, which is made out of 4 strokes. One is an isotherm, so the temperature is kept fixed and equal to T2. One is an adiabat, the heat exchanged is equal to 0. The second one is an isotherm at temperature T1. And the fourth one is an adiabat. Again, don't get confused on this point. This is one particular reversible engine. There is a Carnot theorem, that is the story I explained you before, and a Carnot cycle. Carnot cycle is a specific cycle. There are other cycles that have the same efficiency, okay? Not only the Carnot cycle. Anyway, so now I take this thing and I operate everything in a reversible manner. So all transformations are reversible transformations. Okay? This is very important. Which means in practice that I'm doing things very slowly. Well, in a sense. Actually, no, this is not entirely correct. So let me take it back. For this case. Well, in a sense, it is correct. Anyway, now let's calculate the efficiency. So in order to calculate the efficiency, what we have to do is to calculate the heat and the work that was done in all 4 strokes of the transformation. So the work on the step AB has to be equal to the heat exchanged on the step AB. Why? That's a good idea, but why? So what happens? There is no change in internal energy because for the ideal gas, the internal energy depends only on temperature. And therefore, if you don't change the temperature, nothing happens. All right, so now the work, AB, is equal to integral between A and B of P dV. And now, well, now we use the equation of state, and this comes to be nR times T2 integral A and B of, sorry, dv over v, and it is equal to nRT2 log of VB over VA. You see, I wrote on purpose the correct log. ln, not log. I didn't use the. All right. Now, second stroke, adiabatic.
Hello.
Yes?
May you please first return the previous page?
Sorry, I cannot hear you. Just a second, let me increase the volume. Can you repeat the question?
May you please return the previous page for a while?
Yes, here it is.
No.
Tell me when you're done.
Professor, so when you're proving the number one statement, it says that
Okay.
suppose there is an engine with efficiency higher than
Mm-hmm.
Carnot efficiency, then it violated the Clausius second principle,
Mm-hmm.
which is you cannot
Transfer
transfer heat from a colder reservoir
to a warmer.
Except you do some work.
No, that's the point. I mean, no, that's the overall. Since I'm I'm putting the two engines in a chain. I'm using the work done by one. The work of one is used on the second. So overall, I'm not doing anything. I'm not doing any work overall in this transformation. The net work is zero. And therefore, the only thing I've done is transfer heat.
So, okay, it's not the case of refrigerator.
No. It's not the case of the refrigerator, because in the refrigerator, I have to pay for that work. Think about money. You don't make mistakes. Think about how much you have to pay. That's very sensible, right? So for this engine, you're not paying for this work because it's done by the engine itself. It's just using one piece to do work on the other. So the net transfer is just self-generated in a sense. It's not done by some external person putting a plug in a wall. That's what is wrong about it. All right, so adiabatic. Can I now move on? Yes, adiabatic. So in the adiabatic part, then of course the temperature is changing, and since it's an adiabatic expansion, the system is cooling down. And now the heat exchange with the external environment is equal to zero, of course. Now, WBC is equal to what? Is Rn times R integral BC of T dV over V. I'm putting T in and the volume because T is going to depend on, it's not constant anymore, right? It's not like an isotherm. And now let's consider the following thing. We know that T times V to the power gamma minus 1 is constant for an adiabatic transformation. And therefore, this differential is equal to 0. But this differential is equal to dt v to the power gamma minus 1 plus gamma minus 1 v to the power gamma minus 2 dv times t. All right? And therefore, overall, I get t dV over V equal to minus dt over gamma minus 1, correct? Right? You agree? Yes, good. Excellent. Therefore, if I take this stuff, let's put it in a frame, right? Then I do this. Resize. I make it small. I put it here, and I plug it in this integral. You see how nice it is? Then I get that this is equal to minus n times r divided by gamma minus 1 integral between b and c dt. And this is minus n, this is plus nr divided by gamma minus 1 t2 minus t1. Now, let me now make another little thing here. So n times r is equal to Cp minus Cv, right?
Yes.
Gamma is equal to Cp over Cv, right? And therefore, n times r divided by gamma minus 1 is equal to what? Is equal to Cv, right? Correct?
Yeah.
So in practice, what I discovered is that the work done is Cv times the difference in temperatures.
Yeah.
Right? And this is obvious, right? Because remember, if I well, it's obvious. It's connected to the fact that the change, exactly, the change in temperature is yeah. So the work done is equal to the difference in internal energies, right? And how do you calculate the difference in internal energies? You simply take Cv times the difference in temperatures and nothing else. All right, so now, since I discovered this wonderful tool, let me do it again because I think it's great. And we plug in this, and therefore we discover Cv T2 minus T1. Okay? Now, then we have the third stroke, which is again isothermal. In the third stroke, you have WCD equal to N times R T1 log of VD over VC. You can derive this in the same way we derived the previous one, right? It's obvious. And is equal to QCD, which is not quantum chromodynamics. Okay? And then 4 is adiabatic. So adiabatic is QDA n equal to 0 and WdA equal to n times R divided by gamma minus 1, T1 minus T2. Therefore, okay, so let's now put things together. Total work.
0.
0? Are you sure?
No.
Yeah, that would be very disappointing.
The adiabatic part is 0.
You know, the engine, the engine in which you just spend money, but you do nothing. Well, you know, if you go to the swimming pool quite frequently, you see people who do exactly this, right? They just move like crazy, but they don't go forward because they spend all their energy doing nothing. Actually, sometimes I think that some of them could go in the opposite direction. And anyway, yeah, again, I mean, now I'm not sure you can go to the swimming pool now. But, you know, quite frequently here in Trieste, you can see many of this kind of.
Is there a swimming pool around?
There are trillions of swimming pools. I mean, people go to, you know, I mean, Triestinos are crazy about sports. You know, they're just doing that. They're working and doing that. But they love sports, so just check it out. I mean, it's full of swimming pools here. Beautiful ones as well. The Bianchi is big. It's nice.
Maybe I'll climb it.
Anyway, okay, let's stop on the swimming pool. I can tell you, okay, well, let's finish this. So the work is WAB plus WBC plus WCD plus WDA. Now, as you mentioned correctly, the two adiabatic parts cancel each other, right? So this one cancels this one, and therefore you're left with the two isotherms, which are nRT2 log of VB over VA plus nRT1 log of VD over VC. Now remember that we were dealing with adiabatic transformations. So T1 VC gamma minus 1 is equal to T2 VB gamma minus 1. And T1 VD gamma minus 1 equal to T2 VA the power gamma minus 1. This implies that T1 over T2 is equal to VB over VC to the power gamma minus 1 equal to VA over VD to the power gamma minus 1. And therefore the ratio of the two volumes are identical, right? So, which in practice implies that the work, the total work, is going to be N times R times T2 minus T1 log of VB over VA. Now we have to figure out what is the money. Where is the money? Okay? So where is the money? Well, the money is where I take heat from the warmer reservoir, and that's the first stroke of the transformation, this one, right? And therefore, I have that the money is Q is equal to Q, sorry, is equal to N times R T2 times log of VB over VA. Therefore, finally, the efficiency, if you take the ratio of these two, comes out to be T2 minus T1 over T2 and is equal to 1 minus T1 divided by T2. Okay? So this is the final result. Yes.
That QAB.
Yeah, it's QAB, of course. Yeah, absolutely. QAB.
Why only QAB, not Q total?
Because I have to, the efficiency is W divided by Q2, and Q2 is the heat that I'm extracting from the warmer reservoir. It's not because the difference, right, is the work itself because of the first principle of thermodynamics. Good. Excellent. My poor nose. Okay, so I wanted to actually comment a bit on this. I told you before that if you have an engine and you try to make it reversible by moving quasi-statically, that is not going to be a very efficient engine. I mean, it's going to be efficient. Perhaps it's going to have the same efficiency as the Carnot efficiency, but it's a waste of engine. Why? Because what matters for an engine, for a car, right? It's not, how much work you do in a cycle, right? But it's how much work you do per unit time. What is the power that the engine is able to release, right? So that's very important because, again, depending on the power that your car is able to release, you pay taxes. I mean, at least in Italy. So it's fundamental. It's a fundamental measurement of the efficiency of your engine. Sorry, guys. Anyway, so what I wanted to say is, therefore, that thinking about efficiency only when you're dealing with practical engines is not the end of the story. What you should think about is the engine that has the highest efficiency at maximum power, right? That's the useful thing. So the engine with which you can maximize the efficiency and the power together, right? These are the two figures of merit for a real engine. But we don't care because we are still in the mood of thinking about the general thermodynamic statements. I'm just telling you, well, if instead of being a physicist, you would be an engineer, you would rather think in these terms, or if you had to pay taxes. Now, another important statement is the following. Yes?
Should the efficiency should always be inferior to 1?
Yeah, unfortunately.
Why?
Why? Because life is bad and terrible. It would be fantastic to have an engine with an efficiency equal to 1. But if you think for a second, what statement of the second principle of thermodynamics would an engine with efficiency equal to 1 violate? What? Kelvin. right? It would violate the Kelvin statement. Why? Because the efficiency is W divided by Q2. But W is equal to Q2, because of first principle of thermodynamics, is equal to Q2 minus Q1, right? Now, and this is equal to 1 minus Q1 over Q2 in general, right? And therefore, you see, if I have an efficiency equal to 1, it means that Q1 is equal to 0. So I'm taking heat from a warm reservoir and doing work. The pen is jumping up the table. Now that reminds me, the hickory dock and all this. And anyway, absurd happenings. It doesn't happen. So you cannot have efficiency equal to 1, right? By the way, look at your formula for the Carnot engine. The fact that the efficiency cannot be equal to 1 sets for you an absolute temperature scale, right? In which the temperature, the minimum temperature is equal to 0, is the Kelvin scale, right? And is the absolute 0 that you can never reach in practice. You see? So all of this is all connected. By the way, if you read Wang, you can find there he is using Carnot engines to set the temperature, the Kelvin scale, and all kinds of interesting things. I'm not going to do that simply because you have probably already done it. And I'm too practical to start drawing Carnot engines, chains of Carnot engines to set the temperature scale. But it's true. I mean, you cannot have 1 as efficiency. It's too bad.
Sorry, sir. Just a trivia question. What is the name of the Greek letter for efficiency?
Eta.
Oh,
Eta.
oh.
Eta. Eta if you're Italian. Eta if you're speaking English. Anyway, whatever. Greeks probably say eta. Anyway. Okay, so it's clear. No efficiency equal to 1. Too bad. You always have to waste money. There's nothing you can do about it. All right. So now I promised that that the story that Carnot engines, and that all reversible engines have the same efficiency, operating between 2 temperatures are going to have the same efficiency. Now, in order to see this in practice, let us work out another cycle. It is called the Stirling cycle. I don't know who is Stirling, but what?
Stirling approximation.
Is the same guy?
Oh yeah, that's one.
I don't know. I mean, I have no idea. Absolutely no idea.
And times logarithm.
Yeah, no, that is fine. But I suspect one was a mathematician, the other one was not. But maybe it was the same person. I don't know. I mean, I will check it out. I could check it out on my phone now. Stirling cycle. So the Stirling cycle is different from the Carnot cycle only in 2 strokes. It has, again, an isotherm. And then, instead of having an adiabath, you have an isochore, and then another isotherm, and then another isochore. So this is A, B, C, and D. This is T2 and this is T1. These are the two other
Isochord.
isochord. What?
How to spell isochord?
Isochord.
Oh. It's Silva.
Isochord. I think it's correct. Yes. Okay. Now, let's work out the four strokes. Number one, we have already done it. So WAB equal to QAB equal to nRT2 log of VB over VA. Now, the second one, there's no work done. WBC is equal to 0. And QBC is equal to CV T1 minus T2. Third one, WCD equal to QCD and our T1 log of VA over VB. And then fourth, WDA equal to 0. QDA equal to CV T2 minus T1. Okay. Now, well, the work, of course, is the sum of these two terms, which is going to be, as usual, equal to N times R, T2 minus T1, log of VB VA. Now the the efficiency is going to be, just a second. Is going to be equal to W divided by QAB. And therefore, you get again 1 minus T1 divided by T2.
How do you get QBC?
Yeah, I was thinking about that. QBC is negative. So that's heat that is released, right? QDA is positive. I think that overall it's because QDA is equal to minus QBC and therefore they cancel each other. So that's really, I mean, an isochord I'm getting confused. QBC. Just a second. Okay, let's move on for a second, and then we come back here at the end of the lecture, okay? Because your question is a reasonable question, of course. Okay, so let me finish with the last cycle I wanted to do, and then we go back to the steering cycle. The last cycle is the Otto cycle. Now, the Otto cycle is made as follows. You have P, V. You have two, it's like the Stirling cycle in which instead of putting two isotherms, I put two adiabats. Okay, so A, B, C, and D. Now, first stroke, 1. QAB is equal to 0, and WAB is equal to N times R divided by gamma minus 1, TA minus T. Because it's an adiabatic transformation, so it's, right? Second stroke, isochord, work is equal to 0, and heat is N times R divided by gamma minus 1, Tc minus Td. You see, since I'm not using two isotherms, I'm not really operating between two given temperatures in this cycle, right? I'm not fixing the two given temperatures and operating between these two temperatures. It's a slightly different type of engine. 3, QCD is equal to 0, and WCD is equal to N times R divided by gamma minus 1, Tc minus Td. And then 4 is QDA equal to N times R divided by gamma minus 1, TA minus Td, and WDA is equal to 0. So these are the 4 strokes of my engine. Okay? Where I used systematically the fact that CV is equal to N times R divided by gamma minus 1. At this point, then, I have that my eta is equal to what? Is equal to the total work divided by Q. Which Q? Well, if you think about it, so here in this stroke, you're not exchanging any heat. Here, you're increasing the temperature, right? Because you're increasing pressure in a system at constant volume, therefore you're increasing temperature. P times V equal to N times R times T. So therefore, here you're giving heat on this stroke to the system, and here you're taking heat, right? Therefore, the heat that I have to pay is QBC. And therefore, what I get is that this is equal to 1 minus TD minus TA divided by TC minus TD. We just put in the formulas. You see that W, the total W is N times R divided by gamma minus 1, Ti minus Tb plus Tc minus Td. And QBC is the same thing divided by T times TC minus TB. So that's why I get this formula. And now I have to use systematically these two equations. TB, VB to the power gamma minus 1, and then the other one, TC, VB to the power gamma minus 1, and T d VA to the power gamma minus 1. Now, there is an important thing to notice about this cycle. Before, I was operating between two given temperatures, right? Here, I'm operating between two given volumes, right? Which is VA and VB. Therefore, it makes, while before it made sense to express the efficiency in terms of the ratio of the temperatures, here it makes much more sense to express the efficiency in terms of the ratio of the volumes, right? So therefore, I use this and I find that TD minus TA is equal to TC minus TB to the power times VB over VA gamma minus 1. And therefore, my efficiency, eta, is equal to 1 minus VB over VA to the power gamma minus 1, sometimes written as 1 minus 1 over R to the power gamma minus 1. R is equal to VA over VB, is called the compression ratio. Compression. Ratio. This is, I mean, for us, we're doing thermodynamics because we just want to understand better statistical mechanics. This is not a very important thing. But for engineers, is a very important figure of merit, for example, for cars, right? I don't know if you know, but the difference between a diesel engine, I mean, the diesel engine and a standard gasoline engine are very different. The cycles are different, the way they work is different. But one important difference is also the compression ratio of the cylinders. Okay, and that tells you how efficient are the engines themselves, how good they are, and so on and so forth. How much fuel they're wasting, how much fuel they're using. I think cars like F1 cars, Formula One cars, have actually, enormous compression ratios. I remember once I looked it up. If you're interested, you can check it on Wikipedia. It's something quite interesting. Now, here, okay, I wrote down some numbers. So if you use this formula, for example, you get overexcited, you don't know what to do tonight, and you say, okay, I want to use the Otto formula to estimate the efficiency of the engine of my car. Right? I mean, you could think of doing that. It's not so practical, but so in practice, the compression ratio for an average car is about 8. And the gamma for a mixture of gasoline and air turns out to be about 1.5, 1.4. Now, if you take the eta from this, you will get 1/8 to the power of 0.4, which is about 56%. Now, don't even dream this kind of efficiencies in your car. They're much lower than this. Okay, this is an overestimate. Most of the money you spend for the fuel is wasted. Unfortunately.
There is a car like this.
Anyway, okay, so now let me go back to the previous question because I'm actually confused myself. Why not QAB times QBC? Actually, not QBC, but QDA, right? So here in this cycle, just a second, guys. Pronto? Le posso chiedere cortesemente di chiamarmi fra un quarto d'ora perché adesso sto insegnando in università. Grazie, arrivederci. I'm sorry, but it was an important phone call, otherwise I would have turned off the call. Okay, so what I wanted to say is this. Here, I'm rather confused now because on this stroke, I take heat from the reservoir. From which reservoir? Look, I have to think slowly about this. It's a good question. Let me do it first thing next time. I will give you an answer about this cycle, about why you don't put QBC and QBA. Okay? It's a reasonable question, and I'm confused myself about the result. So I want to think about it slowly again. Yeah, he's asking why in the denominator here you don't take a W over, just you take only W over QAB, not also over QBC and QDA, right? Or the difference or whatever. Let me think about it. Okay, it's not clear to me at the moment.
How you derive the QBC?
The QBC is just the difference in internal energies, right? You're not doing any work, it's just difference in internal energies, first principle of thermodynamics. Okay, let me think about it. I'm confused, might be something trivial. Let's again. I owe you 2 answers. One is this one, and the other one is the difference between quasi-static and adiabatic. Okay. So we will start with that next time. Okay, guys, thanks a lot, and we'll be in touch next Wednesday. Okay? Excellent. Sorry?
I was immersed, so I didn't think that.